spectrum of highly rotating.
So first of all, thank you, Robin and Christopher, for setting up this very nice workshop, which I enjoyed a lot. So this talk is it's going to be based mostly on 3 recent papers with Marina, who you all know, and Guido, who is a postdoc in Barcelona. So to moderate this work, just state some basic facts that we don't know. So we are living in the gravitational wave era. Now we are measuring the gravitational waves produced by mostly black hole mergers, but also neutron-star mergers. And we know that in the future, in the coming decade or so, we will have a new generation of detectors which will be much more sensitive, and this will allow us to test general relativity in an unprecedented way. So this is the question in which I'm interested probing the fundamental nature of gravity using these experiments. So why is this possible? Well, I'm interested in the case of black hole binaries, and essentially this is because a black hole is an object made out of gravity. It's a pure gravitational object, and therefore black hole binary is also a purely gravitational system, and by measuring the waveform produced by these events, well, we can check if indeed this coincides exactly with the prediction of general relativity, with the prediction of this equation, Arminium equals it. And we can do this by comparing the different parts of the signal, the spiral, the merger, and the ring. To this talk will be based mostly on basically on the last part, the ring. Okay, and there are 2 different ways in which these experiments allow us to test general relativity. And this can be seen in this diagram, in which we have different experiments in this plane, in which we have 2 parameters. The horizontal axis is the gravitational potential, so essentially you have a mass m, and you are measuring gravitational field at a distance L, which is just m over. And the vertical axis is the curvature scale, okay, which is a different combination of mass and so as you can see, the classical tests of GR, like the precession of the perihelion of Mercury, is a point of small gravitational potential, so it's weak gravity, and also relatively small curvature. On the other hand, if we go to gravitational potential of order 1, this is precisely when we measure what happens near the horizon of a black hole. This one is called strong gravity. This is what we can measure with gravitational wave detectors. And especially in the case of gravitational wave detectors, which are ground-based, we can measure larger curvatures, okay? Because we measure smaller black holes, have larger curvatures, so that's why this rectangle is at this edge of the diagram. So essentially, measuring bigger gravitational potentials is testing the nonlinear regime of general relativity, and going to in the vertical direction, essentially is testing GR in different scales. Okay? And a very natural question is if general relativity remains valid at all these scales. Okay? Since this is a regime which is still unexplored, very starting to explore it, it's a natural possibility to consider whether we could see this. And okay, what type of new physics? Everybody can have a different favorite theory. But what I will consider in this talk is an agnostic approach to capture the effects of new physics, which is effective field theory. Okay, so if we assume that gravity must preserve the symmetries of general relativity, so diffeomorphism invariance, is a theory for the metric tensor, then the only possibility to extend general relativity is to add higher derivative corrections, higher curvature terms built from the Riemann tensor or its derivative. And this is a schematic way. Later I will show you specifically what are the terms you can include. They can only a few parameters. Okay, so as I said, this is a very general approach. We only assume the symmetries of general relativity and that there are no extra degrees of light degrees of. And another important reason, set of reasons to consider this theory is that well, it's practical reasons. First, this kind of extension of GR, they are still not ruled out by other experiments. I mean, essentially the bounds that we can put on this parameter. This L is at a length scale of near physics. The kind of constraints we can put with gravitational waves cannot be put with other experiments. On the other hand, this extension of GR, they have full predictive power. So as long as this correction has more, we can predict exactly how the waveform is going to be modified. This is also something very non-trivial that we cannot do with other approaches. And finally, well, these theories can actually be tested with gravitational waves. We have extension of GR, but it doesn't give us any modification in gravitational waves. We couldn't see, but in this case, we can. Okay, so it's interesting from a fundamental point of view, but also practical point. Okay. And then focusing, yes.
Is there an estimate on what L should be in order to actually be detectable?
Yes. So it should be on the scale of the black hole radius. That's the type of constraints we can have. Of course, we have higher precision, then we can shrink it. That's the goal, to try to put the best constraint as possible. But of course, we cannot reach Planck scale on in this talk we are going to focus on the ring down. So we already heard a lot about this, so I think I don't need to explain too much. But essentially this part of the signal is, after we have the post-merger black hole, is controlled by quasi-normal modes, okay, which, as you know, are modes with specific frequencies, which are complex, so they have certain decay times. And what is interesting is that the full quasi-normal mode spectrum of black holes is completely determined by the black hole geometry themselves and the underlying dynamics. Okay, so for instance, in general relativity, because we have the no-Hertz theorem, all black holes are Kerr black holes, the full quasi-normal mode spectrum is just determined by two numbers, which are the black hole mass and speed. So all these frequencies are functions of two numbers. So measuring several of them, we can test if GR is correct. So this is what is called black hole spectrum. Now, in extensions of GR, and in particular in these EFT extensions, it is still true that the full spectrum is determined by the mass and angular momentum of the black hole. However, the way in which these frequencies depend on those numbers is different. We have some modifications. So the challenge is actually to obtain what are the corrections to the Kerr quasi-normal frequencies, to obtain this as a function of the parameters of the Lagrangian, so that we can constrain these extra parameters with observations. That's it. And it's a very complicated question, as I will explain a bit later. But in this talk, we want to do something a bit more specific, which is the case of near extremal black holes with very high rotation. And this case is particularly interesting for two reasons. So first, these black holes, they have a long ring. So here I'm comparing the signal of two black holes, one with a spin of 0.7, which is a typical case for most post-merger black holes, and the signal looks more or less like this. You have a spin 0.99, you looked at later one below, as you can see it's much more long-lived, and there are way more oscillations. So it means that if we ever detect one of these black holes, we can measure this signal much better, and therefore we can put much better constraints on, well, we can test GR much better and put the constraints on modifications. And on the other hand, it turns out that black holes near extremality are sensitive to new physics. So as Marina explained the other day, if we are very, very close to extremality, we have quantum effects that become relevant. Although for astrophysical black holes, we will need to go super close to extremality. This is much closer than we can expect to be. However, this mechanism that is there. But recently it has also been understood that also classical effects become important. They grow when you are close to extremality. Okay? And with classical effects, I mean precisely the higher derivative corrections. So for instance, in these papers by Horowitz and collaborators, they showed that perturbations of extremal black holes in the CFTs can develop singularities at the horizon. It's also known that in certain theories, extremal solutions themselves are singular. So this implies that if you are very close to extremality, somehow you should see a growth of the corrections. But it's still not very clear what are the observational implications. So the question we ask is, what are the actual signatures in the ring down of higher derivative terms near extremality? Are there any growth of corrections? So this was the introduction. So the rest of the talk. First, essentially, I will continue with the introduction. I will do a review of the spectrum of near extremal Kerr black hole. Then I will explain some basic properties of quasi-Riemann modes in EFT extensions of GR. Then I will focus on a particular theory in which we can do computations for exact in the angular momentum of the black hole, and then I will show you what happens with the quasi-Riemann modes. Okay, so let me review the spectrum of near extremal Kerr. So that we are all in the same page, I remind you this is the Kerr metric, and it depends on two parameters, m the mass, a the angular momentum per mass, and the extremal limit is when a equals n. So we will also introduce this this parameter epsilon that is very small when we are in the near extremal region. We are never interested in exact extremality, only very close to it. Okay, but what I will say in the next 2 or 3 slides is actually general, not only for near. So what we need to study quasi-normal modes is not only the background, but of course to study the perturbations. We put the metric perturbation on top of the background, we study the equation and so on. The thing is that this cannot be done, it's not very practical to work with metric perturbations directly. Instead, the key result is the Tucholsky equation, which is a decoupled equation for perturbations of the biotech. So it's an equation that is satisfied by a component of the perturbed by tensor on top of the Kerr band. I'm not writing it explicitly, but it's this operator op. And as I said, it's a second order decoupled equation, which is very remarkable. On top of that, this equation is separable, so we can consider an ansatz like this. And we have to solve for these two functions, it's the angular and radial functions. So the angular functions, they have a name, they are spin-weighted spheroidal harmonics. And essentially, you solve it, and the equation gives you a certain separation constant. And with that, you can find the radial equation, which is the theme which we will focus. The key result is this equation, where we have B, which is an effective potential. Of course, this equals 0. Okay, so once we have reduced everything to this single equation, the quasi-Riemann modes are defined as usual as the solutions that are outgoing at infinity and inflowing towards the horizon. So this is the potential as in terms of the tortoise coordinate, and usually have this form with one peak. And as we know, this type of problem only has solutions for a discrete set of complex frequencies. Now, this is how to define the quasi-Riemann modes, but another question is how to actually compute. So to do that, I'm going to focus on a particular regime, which is going to be useful for us later. It is the agonal regime. It's when L, the harmonic number, is large. So in this case, the potential, the Stokowski potential, reduces to this expression, where this is a dilemma, the angular separation constants I mentioned earlier. And it turns out, here we can compute the Quasi-Riemann modes just by looking at the maximum of the potential using the WKB approach. So the real part of the frequency is found just by extremizing the potential. We find the point where V and the derivative are zero. This determines the real part. And then the imaginary part is given by this explicit form. Okay, so you can find analytic results for the Quasi-Riemann modes. And of course, this regime is not the one we are most interested for observations, but it gives, the idea is that it gives an approximation for the QNMs, even for Lowell, and it captures general features of the spectrum. Okay, so just a remark for the rest of the talk. We will usually use this parameter mu, this m over capital L, find like this. So this because this is the expansion parameter in the agonal regime. And m is the harmonic number. Okay, so applying these ideas, what we had to do. So all of that, by the way, all of that was in general for curve. We weren't focusing on the near estimate case yet. Now we are going to focus on that case. So what we have to do is to look at the maximum of the potential, and the question is what happens to this maximum when we approach the extremal limit. So there are two cases, depending on this parameter. So when mu is above a certain critical value, which is around 0.74, it turns out that the maximum of the potential approaches the horizon at the extremity. So you can see the potential here, and this is for these values of mu, and you can see it has the maximum at the horizon. If you compute the corresponding Quasi-Riemann modes, it turns out they have vanishing imaginary part. When you approach extremality, the imaginary part goes to zero, and therefore they are called zero-damping modes. So they are very long. Okay. On the other hand, for mu below this critical value, the maximum is located outside the horizon. As you can see, changes the behavior. Now the horizon is a minimum, so it's not captured by the WKB method. And instead, you have to use this point. And this gives you modes that have a non-zero imaginary part, so they are damped, and they are called damped.
Sorry, shouldn't you have a local minimum from the modes? So is the local minimum?
No, these long lived modes are related to the fact that you are near the horizon. They live in the near horizon region. So essentially, it's like they are infinitely redshift.
So they would be imagined with maybe a far larger than this.
The minimum is the horizon itself.
Is it a minimum?
There is nothing after, so but is the low? Yeah, it's a local minimum.
Yeah, here I'm putting it as a function of R. If you put it as a function of the tortoise coordinate, the coordinates are infinite. So it's never exactly at the horizon. It's very close to the horizon.
Sorry, when the maximum is close to the horizon, can you still use WKB? Because WKB was assuming that the maximum is in the middle. Somewhere it's not on the on one of the extreme of one of the boundaries where the potential is defined.
Well, I mean, as I said, the horizon is always at minus infinity. So this plot is a bit deceiving when you see like this. It's always infinitely.
No, but it's the maximum. If you go to tortoise coordinate, is the maximum located at minus infinity? Is the function growing towards minus infinity?
No, it goes to a constant.
It goes to a constant. Thanks.
Okay, so these are the results obtained from the WKB analysis. It turns out there are extra modes that are not captured by this analysis. This was figured out by these interesting papers. It turns out that zero damping modes also exist in all the regime of positive mu, okay, but they have to be found using other techniques. So the conclusions is that we have this branching of the spectrum, as I said, discovered by these authors. Zero damping modes, if mu is positive, and they take this universal form where we are close to extremality. Okay, so the real part tends to this, where omega, here capital omega, is the angular velocity of the horizon, and the imaginary part you can see is scaled with the square root of epsilon, so it goes to zero at extremality. And the other half, yes.
Are those the modes that form a half with extremality?
Form a
delta extremality or not?
I don't know. Yes, and we have the damp modes for mu below this value. So there are some values for which we only have zero damping modes, and other values in which we have both types. Yeah, and this can be seen better in this diagram. So this analysis that I was explaining for in the equal limit, it can be done actually exactly to see for which values of L and M we have only zero damping modes or both types. Okay, so these are these triangles. So this region is where we have only zero damping modes. In the blue circles we have where we have both. And these lines, this prediction from the iconal regime given by this. So as you can see, it's very good prediction. It's not exact, but it's good. Okay, so the question we want to ask for the rest of the talk, the main goal of the talk, is to explain what happens when we include higher derivative corrections to this modes. Other questions so far?
Just to follow up on Christophero's comment, I think it means that this would be not zero damped, but there'd be power law decaying in time rather than exponentially.
Yes. So in fact, in these papers, they comment that when you add all of them up, it produces a power law decay.
Yeah.
Okay, so let me then review some aspects of classical modes in EFT extensions of GR. So as I promised, first let me show you the explicit expression for these effective field theories. So up to 8 derivatives, we have 2 cubic curvature terms and 3 quartic curvature terms. Okay? There are no quadratic terms because they are either topological, the Gauss-Bonnet invariant, or can be removed via field definitions. Okay? Like Ricci square can be removed if you define the metric. Actually, it doesn't even modify the solutions of bulk in general relativity. So in this perturbative approach that we're considering, and some of these violate parity, like R3 tilde, and also this one, because well they contain this dual Riemann tensor. Okay. So the goal is to find the rotating black hole solutions in these theories, a linear order in the couplings, and also compute the corrections to the quasi-normal modes. Yes, this is what it was. Okay, but this is a really complicated problem for several reasons. So first of all, it turns out that the backgrounds of the rotating black hole solutions are not even known analytically in these theories. And I mean, not even the perturbative correction. So this already complicates things a lot. So we have available some approximations like expansions in the angular momentum. There are some numerical approaches, but there are no closed form analytic solutions. On the other hand, we know that these geometries are not of Petrov type D. So I didn't explain this, but this just means that the form of the Weil tensor is very simple. In the case of Kerr spacetime, is of this type. But because here is not of Petrov type D, what happens is that we don't have the Dubrovsky equation. Okay? So again, we don't even have a simple equation to study perturbations. And in addition, we know that wave equations in these modified backgrounds, they are no longer separable. They don't have the property of half-work. So all of this makes the study of perturbations really complicated. So, despite of this, there has been quite remarkable progress in recent years with several methods that have been introduced. So, on the one hand, there have been several proposals for modified two-Gaussian equations. So they aren't as nice as the original two-Gaussian equation because they are still coupled to other components of the metric perturbations and so on. But one can work with them and one can solve them and find quadrilateral modes. And so far, these equations have been solved using spin expansion. One can evaluate them using this spin expansion of the black hole metric and find an explicit but long expression for the modified two-Gaussian equation, like a single radial equation. And only very, very recently, this actually was from last week, in this paper by George Santos and William Boyce, they found, well, I think they evaluated these equations using a numerical background, and they were able to obtain possible modes for very large rotation. This first paper has done this for even close to extremality. On the other hand, there are also spectral methods that have been proposed, and here the idea is just to solve the full modified Einstein equations numerically using this spectral decomposition. They don't need to use the modified Gaussian equation, but of course more heavy numericals. Okay, so has been important progress, but the high rotation regime is still not fully understood. So what we'll tell you today, later, is a few things that we have learned about. Okay, but first let me mention a few generalities of what happened with Quasimodo modes in these theories. So the first thing that is quite universal is the breaking of isospectrality. So as probably you know, a very important property or very interesting property of Quasimodo modes in asymptotically flat four-dimensional black holes in GR is that they have isospectrality. So essentially we have two families of perturbations that I usually call axial and polar, and in principle each of them could have a different set of Quasimodo mode frequencies, but it turns out that they have identical spectra. So for instance, this is this common frequency for curved black holes as a function of the angular momentum. This is but this is no longer the case when we consider higher derivative corrections. Basically, in all the theories we consider, this is broken, so you can see a difference between Quasimodo modes for axial and polar sectors. Okay. So, to show you a specific example, this is the leading correction to GR, the cubic corrections. Well, at leading order in the coupling constant, we can expand the frequencies like this. So what I'm plotting here is these are dimensionless coefficient, okay, that only depends on the dimensionless spin of the black hole. And this is the corrections to the real part and to the imaginary part, to the polar and axial sectors. Okay? And this is obtained using this technique of spin expansion that allows us to obtain a modified radial Gaussian equation analytically. And this is obtained using expansion to order chi to the 18, so we have many terms. And well, as you can see, this is at this order that allows us to go up to a spin 0.7, but to go beyond, we will need to add more terms, and it becomes very, very complicated. And by the way, more results for all the theories that I showed and for many other modes, including overtones, can be found in this repository. Okay. So the question is, how would this continue to happen? Right? But to answer this, let me consider this question, which is going to be interesting for us. So most of these theories, or basically all of them, break isospectrality, but is there any theory that preserves it. So it turns out there is no theory that preserves isospectrality in an exact way, but there is a notion of isospectrality that can be preserved, which is isospectrality in the econal limit, precisely in this region of large L. And we find a single theory that has this property, and it's this quartic extension, the sum of these two. Okay.
So is there a way to understand on which ground, general grounds, is isospectrality supposed to be broken or not? Or it's just
We don't have we are not sure. I mean, this could be probably understood as some symmetry, and this is something we want to explore. In fact, the work done by Sasso, I think, was very interesting. So perhaps this could be related to S duality or something. We still don't know. Yes, but for this talk, this will be useful because, as we're going to see, it gives us simpler equations. So this is the unique extension that preserves isospectrality and in the econal limit. And this is here I'm plotting the corrections to the real part of the frequencies for plus and minus polarizations. And this is the 2, 2, 3, 3, and 4, 4 modes. So as you can see, for low L it's not exactly isospectral, but it's already, the isospectrality region is already very mild. And the exact statement is that this ratio goes to 1 and L goes to 1. This is what can be proven. And the reason why this happens, we found it's related to this other property of the theory. That if you study the dispersion relation for gravitational waves at large momentum, this is equivalent to the econal regime, we find a dispersion relation that doesn't depend on the polarization of the wave. Okay? So for any other theory, for instance, if I put here a different coupling, what I will find is that this expression depends explicitly on the polarization term. But here it's not. It's totally independent. So it's the only theory that is non-birefringent. So the speed of gravitational waves is independent of the polarization. And this can be connected to isospectrality. Why? Well, there is a known correspondence in general relativity. It's a known correspondence between econal quasi-normal modes and the photon ring geodesics. Okay? So the photon ring is the set of unstable closed orbits around black holes. And it turns out that the real part of quasi-normal frequencies is given by the orbital frequency of the geodesics, while the damping time can be computed as the Lyapunov exponents, so the instability time scale is geodesics. But the reason there is this connection is precisely because in GR, gravitational waves of large momentum move along geodesics, and quasi-normal modes are nothing but gravitational waves. In these extensions of GR, we still expect a correspondence between quasi-normal modes and unstable gravitational wave orbits around black holes, but of course these orbits are no longer geodesics. And in this correspondence, it's quite clear that non-birefringence, which is the propagation is independent of the polarization, is the same as isospectral. Okay? So that's how we can see that this theory will be isospectral for black holes of arbitrary rotation in the economy. So, well, summarizing, we have this theory. This is the one I'm going to focus for the rest of the talk. And just one additional comment is that we found that this is seems to be related to string theory. So you consider the type 2 string theories in 10 dimensions. You compactify to 4 dimensions in the simplest way. You find the same correction. Well, but as I said a moment ago, we still don't understand what is the reason for this. Okay. So now, yes, the strategy to obtain quasi-normal modes with arbitrarily high rotation is we're going to focus on this theory and we're going to consider the equilibrium. So let us study what happens with black hole perturbations in this theory. So the key observation is that we can use this dispersion relation already to study the perturbations. So the idea is to find an equivalent scalar equation that gives us the same dispersion relation. And it's very easy. You just transform this case into nablas, I nabla, and you can write this scalar equation. Okay, so my claim is that this will give us, solving this will give us the iconal quasi-normal modes, gravitational quasi-normal modes in this thing. This is just like in general relativity, we know that a massless scalar field, so that's this term, 0, already gives us the iconal quasi-normal modes, okay, because the iconal limit is universal. Now there's a bit more rigorous way to prove this. One can consider the conditional equations, linearize them and so on. One can show that in the full equations become this disappear. So this is much simpler than using this modified Tukhowski approach. We just have to solve this scalar equation, and also, as mentioned, yes, it is enough to solve it in the Kerr background. We don't need to consider the corrected Kerr background because this term here is dominant in the iconal regime. It has 4 derivatives. Okay? So the leading corrections to the equation almost in the iconal regime, yes, come from this. We don't need to consider modified Kerr, okay, which will give us corrections here, but they're subleading. Okay, so how do we solve? So this equation is no longer separable. However, we can use these spheroidal functions to expand the solution because they are a basis of functions and they satisfy orthogonality relations. So what we can assume is a leading term that is like essentially the ER term, and then a first order correction. Alpha is my coupling constant. Yes, so I can assume this.
Sorry, can I ask you?
Yes.
So on the previous slide, you said that you can drop the first term because you get higher powers of alpha from the second term.
No, we don't drop the first term. So, but it's like here we also have higher derivative corrections entering from the fact that the nabla operator is modified because we have, in principle, a modified background. But these modifications are going to be ordered alpha times L squared, while this modification here is alpha times L to the 4. So if I consider large L,
But alpha times alpha to the 4, is it still a small perturbation, or how does?
yeah, we have to consider a regime which L is large but not too large. So this is not bigger than here. Okay, so there's a regime of validity. Alright, so I was explaining this expansion of the solution, and then, well, we plug this into the equation, and then what we can do is we project on these spheroidal functions, and because they are orthogonal, at the end of the day, we get a separated equation, a decoupled equation for the leading radial function, where we have an explicit correction to the Tukhowski potential. Okay? So it's given by this integral. Now, well, this integral is still a bit awful because it involves these spheroidal functions which are not analytic, and we are in the iconal regime, so they are highly oscillatory, so computing this integral even numerically is challenging. However, we found an interesting way to reduce this integral to an ordinal. Okay, so can be reduced to this. Now we'll have weird functions. There's a quite normal integral. Essentially, can be expressed in terms of elliptic integrals. And well, and that's it. Well, here I added some detail, but I think I will skip it. Just some mathematical result.
Is the integral is in the Larsen regime as well?
This.
Yes.
Yeah, so we are assuming the large L regime to obtain this result. Yes. But essentially, the summary of this is that we have this equation to solve, just a radial equation with this correction, explicit correction to the potential. And then we can apply the WKB formulas just like in general analysis. This doesn't change. So we have to extremize the potential, we find the real frequency and then the imaginary frequency. All this can be done analytically. This, of course, the formulas get quite long, but everything is analytical. And we don't need to do any approximation in the angular model. Then let me show you the results that we get for the Quasi-Riemann models. So just to set some conventions, I will mostly show you this quantity. Again, it's a dimensionless quantity. Well, this actually has dimension of 1 over m. This alpha hat is this dimensionless coefficient, okay, which we assume to be small. And as before, the result will depend on this mu and dimensionless being j over j. Okay, so first thing we check is if this econal approximation gives us a good approximation to the low L modes. Okay, it's a sanity check. And actually, it works even better than expected. So this is the real part, and this is the prediction of the econal formula. And these lines are the computations through using this modified Tchaikovsky equation with the speed expansion and so on. So it's much more complicated. And as you can see, even for already for L equal 2, the real part works quite well with the econal formula. Of course, it should only agree for L going to infinity, but it goes quite well. For the imaginary part, what we can see is that the result clearly converges to the black line as we increase L. Okay, so this blue line is already L equal 5, and it's already quite good. And, well, again, for finding L, the result is not isospectral, but it's converging, both lines are converging. Okay, so this makes us very confident that this approach is right.
So it looks like the agreement is becoming worse at large chi.
Yes, I mean, for L equal 2, definitely.
If I look at the left panel, for all of the curves, right, the agreement becomes worse.
Yeah, but you can what you should see is at a given chi, if the result converges to the.
I understand this, but I'm saying now are you trying to push this to chi close to 1, or will you consider?
Yes. Then I will show you what happens to the black line. Of course, again, the black line, strictly speaking, is only for very large cell. I will expect some quantitative features to be valid in general.
But do you have are there numerical results also at large chi, or are they only available in this region?
This was, when we did it, this was the only result available. Now, last week, there was this paper by Santos and a few students, and it kind of look the same. Okay.
Maybe you said in earlier, there is a mode that seems to get a positive imaginary part.
No, this is the correction. This is the correction to imaginary part.
Yes, that's the correct.
Yeah, so
Yes.
the full thing is still not.
It's stable.
Yeah, because everything is perturbative, so in principle, you shouldn't believe it is true. Okay, so, yes. Exactly, so this is, we compare for modulated spin because what we can do with modified Tchaikovsky, but now this econal result allows us to go to arbitrary spin, actually. So, the results can be summarized here. So here I'm plotting the frequency as a function of mu and for several values of the angular moment. Okay? So the top panels are for Kerr, the real and imaginary parts. And for instance, something you can see here very clearly is that when we are very close to extremality, which is this red line, you have this segment here is essentially flat and essentially zero, and these are essentially the zero damping modes. You have the transition here between damped modes and zero damping modes. Now, if we look at the corrections, something we see that it happens generally is that as we increase the spin, the corrections become much larger. Okay? Both for the real part and the imaginary part. But something that is even more intriguing is that if we zoom in this small interval, it's precisely around this critical value of mu. Because here we can see that for kerr, the imaginary part of the quational modes is very small. But it's precisely where the corrections are maximized. They grow a lot. So it means that if you consider the relative correction, it's going to be even bigger. Okay? So it grows a lot. And we can see this better in this comparison. So here I'm focusing on the imaginary part, and I'm going to plot the kerr result as a function of the angular momentum and this dimensionless correction coefficient. Okay? So for mu equals 1, we have this situation. The correction has a peak here, then very sharply goes to 0. And well, the kerr value is midway going to 0. But if we decrease this mu, what happens is that this peak becomes even sharper and closer to extremality, so that the kerr frequency is even smaller. And if we go, in this case, we are already below the critical value. Well, here what happens is that the correction is maximized at extremality, and the kerr frequency goes to a quite small value at extremality. And if I was closer to the critical value, this is even more steep. Okay, so I think you can see where this is going. The idea is the corrections, the relative corrections can become large if we are near this critical point.
So does this give you a bound on L?
Huh?
Does stability give you a bound on L?
A bound? A
Bound.
bound on L?
Yes.
No, I'm going to explain what happens. There is no instability that we know. Okay. So to analyze this more properly, we have to do also some analytic computations. So for this, we're going to consider the regime in which we are very close to extremality. This is the extremality parameter. And also we are very close to a critical point. Okay? The critical bar is the critical point. But depending on the relative size of each of these parameters, the behavior is different. So I will consider these three regimes. So the first regime is when we are much closer to extremality than what we are to the critical point, okay? And we are above the critical point. So in this case, the explicit expressions for the kerr frequencies are basically what I saw before. And well, I'm not showing the expression of the corrections, but well, by the way, here the only thing you should look at is the epsilon. Okay, it's the red thing. All the other coefficients we don't care so much. But you can see the imaginary part for kerr goes with square root of epsilon, and the correction goes linear in epsilon. So it is sublinear. So in this case, in this regime, the corrections don't change the qualitative behavior of the R. Now, this second regime is more interesting. So here, we are closer to the critical point than what we are to extremality. Okay? So mu minus mu critical is arbitrarily small. We could even be in the critical. So it turns out here the kerr frequencies obtained from the iconal formula, they go with the square root of epsilon, the imaginary part. But if you compute the correction to the imaginary part, it goes with epsilon to the 1/6. And therefore the ratio goes to epsilon with a minus 1/3. So it diverges when epsilon goes to 0. So exactly what we were saying, the corrections, the relative corrections can become arbitrarily large. So the lifetime of the modes could change significantly. And in the third regime, something similar happens. So this is the regime where we are below the critical point. So these are damped modes, but we are very close to the critical. And in this case, what we see is that the kerr frequencies, the imaginary part scale with 3/2, and the correction scale with 1/2. So that the relative correction goes as 1 over mu minus mu. Okay, so again, this would blow up if you are arbitrarily close to the critical point. So summary of all of this is this plot, these formulas. So in the plot, I'm showing precisely the relative correction to the frequency as a function of the spin, and now this is a logarithmic scale. And the different lines are different values of mu. So this dashed line is precisely the critical point. So this shows that if you are close enough to the critical point and close enough to extremality, so this can be arbitrarily large. Also notice this is a logarithmic. So this is great because it means that these corrections are much bigger. If we are near extremality, we have a much better chance to try to detect.
But how much actually the corrections are big if you include the numerical coefficients, like black hole mass or the scale of the higher derivative corrections?
How much?
Yeah, so if you include the physical realistic value of L and capital M, then how big are the corrections?
Yeah, so this is, I'm factoring out the coupling constant. Of course, you have to multiply everything with this coupling constant, which is alpha over m to the 6th. So of course, at the end of the day, the overall scale is set by the black hole mass. But then the question is how much bigger the correction can be relative to that order of magnitude estimation. Okay, so essentially here is like 1,000, 10,000 times bigger than this.
So, but this divergence is telling you that your effective theory is not good, right?
Not really.
Okay.
So actually that's the next thing I wanted to say. So the other question is this a breakdown of the EFT or what is really going on? So to do this, we have to do a non-perturbative analysis of the frequencies. So these conclusions were based on a linear perturbation on alpha. Okay? But given this modified Topolsky equation, we can actually solve exactly for the Quasinor modes without expanding in alpha. And we can see what happens near the critical point. And the main thing to take into account is that actually the corrections modify the critical point. So this critical point is where the potential becomes a saddle point at the horizon. Because remember, it's the transition from the horizon being a maximum to it being a minimum. Okay, so especially when this is seen. So you can compute the effect of the corrections, and they essentially shift the critical point. So you have to be careful with this. And you can actually compute what happens to the frequencies near the critical point. You do it carefully. And they actually behave like in curve. So again, mu minus mu critical, but this is the corrected mu critical to the 3/2. And if you expand this formula, now using that expansion of mu critical, you precisely get what we are getting. And the correction go to 1/2. So of course, if you divide, it seems like there is a divergence. But this is not a breakdown of the EFT, it's a breakdown of the linear alpha expansion of the frequencies, because you shouldn't expand around this point. You shouldn't expand around mu critical if you are too close to it. So a very simple way to see this is again plotting the diagram. So this is what we got for curved black holes in GR, this phase boundary. And what happens is that now we have a new phase boundary because the mu critical changes. So it's this red line, the new one. But this means that the modes in this band, critical band, actually the behavior, the qualitative behavior changes. So in this example, these blue dots, where in GR we had zero damping modes and damp modes, now we will only have zero damping modes. Okay, so it's a qualitative behavior in the spectrum. And this explains why we could actually have order 1 corrections in this regime. Okay, it's not really a breakdown of the EFT, it's because these modes are super sensitive to the change of the criticality condition. Now, another question is, because of course here I'm exaggerating a bit the width of this band. If the corrections are very small, it will be very thin, very narrow, and maybe you don't pick any mode inside the band. You have to go to very large L. But still, this mechanism, this explains why the modes close to the boundary are going to be extra sensitive to the corrections. Okay, this is something that helps. Okay, so the last thing I wanted to say is that due to this, because we understand why the corrections grow, we can actually estimate the size of the corrections also for low L. And essentially, this is because we can describe the modification of the phase boundary exactly in low L. Why? Because this only depends on the behavior of the potential near the horizon and near extremality. This is something that we compute there exactly in this paper. Essentially, all that happens is that these angular separation constants are modified in the near horizon Tchaikovsky equation. So we can estimate the size of the corrections by estimating, so the new phase boundary is given by this condition, just changing the angular separation constants. So the relative correction essentially gives us an idea of the size of the higher derivative effects. So when this denominator becomes very small, which is when the modes are close to the boundary, precisely the effects of the corrections become amplified. And you can compute what happens in the LM plane, and this picks up certain modes that are particularly sensitive. Well, you can see here some darker modes in which these relative corrections, this factor can grow like 10 to the 6, 10 to the 7. So essentially, these are modes in which the relative corrections to the are orders of magnitude larger than for black holes with moderate rotation. Okay, so with this, I go to my conclusions. So essentially, this was the first computation of gravitational quasi-normal modes with high rotation, arbitrary rotation beyond yard. Of course, it's in the economic regime, but still gives us an idea of what happens in this high rotation regime. And the key development was this effective scalar equation for isospectral, this is isospectral theory, but we think a similar approach could be possible for other theories. Now, there are open questions in this particular area. It's like, well, we also would like to know what happens with time domain in this regime where the corrections grow, to see how this reflects in the time signal. And well, yes, as I said, we want to extend this for non-isospectral theories. But the general remarks, which I think is more important, is that the beyond GR effects increase dramatically for high rotation, increase by orders of magnitude. This is what we have seen. And in addition, as I remarked at the beginning, highly rotating black holes have very long-lived modes. We can measure them very precisely. So you would put these two facts together. It means that if we ever measure a highly rotating black hole, this will be a golden event to test new physics. We will be able to put much better constraints on this L scale. We could improve the constraints by orders of magnitude. And yes, this is already mentioned this. So thank you for your attention.
Questions?
Yeah, so and you had this plot where you said that the size of the correction was something of order 10 to the 7 higher than, so like a dramatic size correction. So again, if you combine this, if you use stability as a constraint, does that give you bounds on the Kaplan constants of the high derivative terms?
I think not, because these modes don't become unstable when you have
If delta I is positive, if delta omega I is positive, and you just add them together with a large enough coefficient, then you'll get something unstable. And then you'll say, okay, the coefficient can't be that large.
No, what happens is that when delta omega I, because of the order of omega I, this linear approximation breaks down, you have to use the full solution of the equation, and there are no instabilities. That's what we see. These instabilities could come from other effects, like if the potential develops a potential well or something like that, but that's something we haven't explored. But in principle, from this, I don't think there will be instabilities.
But presumably for large enough Kaplan constants, something goes wrong.
Yeah.
Eventually, something will be stable. Okay.
Do you have an estimate of the nonlinearity effect? So here you're solving the equation for the linear perturbations. So in this regime where the collections are big compared to the leading order results, one might worry whether quadratic or higher nonlinearities can be relevant. So do you have an estimate?
No. We don't have them. But in any case, I think with the quadratic quantitative modes and so on, at the end of the day, one should have a full waveform which one incorporates all the GR effects, and then one can add this to that. So that
The question is if one can trust the linear perturbation theory results or not.
I think I don't see any reason why one cannot trust it, because as long as the amplitude is small enough, you can always neglect the quadratic terms.
Any more questions?
No.
That's time. Pablo?